All right, so chapter 4, we're going to cover chapter 4 now. This is going to be propagation, antennas, and feed lines. We're just going to do the first half of that. All right, so there's a bunch of questions in here. I'm just going to go over a couple of them and just give you some of the answers, and then we'll discuss them a little bit. 4-2 shows you some diagrams. In fact, I'll just start with that one, actually. 4-2, you got a signal source, okay? This is just your straightforward, like, it's called an omnidirectional antenna, just like a wire, a pole sticking up in the air. So that pole is going to radiate the energy, like you see here, just like a bunch of circles. So it just, let's say this was my antenna. It's going to radiate like in circles all the way around. It's just like throwing a rock into a pool. So you throw the rock into the pool and it produces ripples equally in a circle, starting small, bigger and bigger. So the further out from the rock you get, the smaller the waves are going to be. Okay, it's the same thing with radio waves. So if this was my HT, my hand transmitter, my small radio, and if I talk on it, the antenna's pointing up, it's going to radiate equally all around me, this direction all the way around. So the further out it is, the weaker the signal. That's why the further away you go, the harder it is to receive signals. So let's see here. All right, so I'm going to give you just one of these questions and answers. T3A07, about in the middle on 4 propagation. It says, what weather condition might decrease range at microwave frequencies? So there's different frequencies that we talked about, UHF, VHF, for example, and HF. Those are the 3 main ones that most people need to know about. VHF and UHF, you will get a license for that with your technician. The HF, you have to go to general to get voice permission on that frequency. So VHF and UHF have different properties. VHF can go longer across the horizon. UHF just is more line of sight. It's a higher frequency. And so what happens is with rain or fog, it can actually absorb the UHF frequency. So all your cell phone towers and the frequency they communicate on are UHF frequency. So if there's more rain or fog or snow or any kind of precipitation in the air, your cell phone reception might not be as good because it's absorbing those frequencies. VHF, on the other hand, doesn't get absorbed as much by that, so it's not as much of an issue. All right, so I think I'm just going to talk about propagation and how waves propagate. I'm going to skip forward so I can talk about some of these concepts. On 4-4, there's a good example of these 4-4 and 4-5. Okay, so 4-4, we're going to talk about the layers of the Earth's atmosphere. Okay, so on figure 4-2, they have the Earth and the different layers of atmosphere. Okay, so first you have the first layer, you got where your clouds are down below. And your next layer is called the stratosphere. The stratosphere is anything from 6 miles to 30 miles. So it's your lowest level, okay, it's the stratosphere. There's a stratosphere balloon, they go in the stratosphere, that's your lowest layer. Then from 30 to 60 miles is your D layer. 60 to 70 miles is your E layer. Then you have an F1 and an F2 layer from 70 to 140 miles up in the air, and then 140 to 200 is your F2 layer, and then you got outer space. Okay, so F1 and F2, the reason they're F is because these layers combine at night, and they separate during the day. So what happens is, as the Earth rotates, the sun rays hit the atmosphere. And when it hits the atmosphere, it kind of like, it moves the electrons and puts them from one side to the other, and it's called charging. So it charges the atmosphere. So for example, the old fluorescent light bulb tubes that they had, there's fluorescent gas, and there's 2 little wires on each end. You put electricity through them, and it charges the gas, and that makes it light. That's what makes it light up. So compact fluorescent light bulb, same thing, only with little swirls in it. So if you introduce a current into the gas, it charges it up and produces light. So the same thing happens with the entire Earth, only you just can't see it as much. It'll charge this layer up, and then at night it discharges, and then it's just like one layer. So in the day, for example, AM radio signals don't transmit as far, but at night they transmit further. Now, the E layer, this one is very interesting. This is kind of this middle layer in the sandwich. What will happen is it can do what are called skipping or hop E layer. It's called E. What is the word? I'll come to it in a minute. I think it's called E skipping or something. All right, so I'm going to go to, yeah, it's sporadic E or E skip. Okay, so what happens is, to explain it, I got to go to the next page. 4-5. Okay, so 4-5, figure 4-3, they've got an example of a radio station over here and one on the other side of the Earth. So if you see the Earth has a curve, and you can't transmit straight across because you'd be going through the Earth, right? So you can't get radio signals that way. Did you run out of memory or something, Palmer? On the GoPro? It stopped. I don't know if it's out of battery or it got too hot or ran out of memory. Can you look at it? Okay, so here's the example. The basic concept is the frequency of the radio wave determines whether or not it's going to bounce off the atmosphere and go down, or whether it's going to go straight through it. So if you want to go from this station to this station, you can actually aim it towards the sky at this angle, and if it's the right frequency, it'll bounce off just like a mirror in the light. Just think of radio like a light. It'll just go up here and bounce off the atmosphere and go back down. So this allows you to transmit over long distances. And the E wave, the E layer can go 1,200 miles or more. Depending on the frequency, you can go even further. But if the frequency is too high, like UHF is ultra high frequency, it'll go straight through the atmosphere. If it's too low, it will just get absorbed. If it's just right, the Goldilocks zone, not too hot, not too cold, just right. If it's just right, it'll bounce off, and that allows you to transfer farther. Okay, so this whole layer from 30 to 60, all the way from here to the top, that's called the ionosphere because it's charged by the sun. So what'll happen is you can get, it'll actually, in layer E, if it's just right, it'll go through the D layer in the stratosphere, but it's not high enough to penetrate to the F layer. And so it will go back down, and once it gets up here, it'll get stuck between the E and the D, and it can kind of go back and forth like a pinball machine, up and back and forth, and it does skipping and hopping, and it'll go up to 1,200 miles. And when it loses enough energy, it'll come back down out, and you can receive on the other part of the Earth. So, so it's called sporadic E. So anyway, so that's kind of a little bit of the ionosphere and why it's important. There is some specifics they tell you about. So for example, the HF or high frequency, which is the lower frequency than VHF and UHF. Also, well, HF bands such as, okay, I'm going to go 4-4 about in the middle. It says, during the years of maximum solar activity, the upper HF bands such as 10 meters are likely to be open from dawn shortly after sunset. Occasionally, the F layers can even reflect 6-meter signals at the sunspot's peak cycle. Okay, so let me tell you what all that means. Okay, so the sun has a cycle. Like we have a 24-hour cycle that, you know, the Earth rotates around, and then the moon has a 28-day cycle or whatever, and then the Earth 365 days where it rotates. Well, the sun has a cycle also, and its cycle is measured in years. So it has peaks of high intensity and low intensity, and it's an 11-year cycle. So every 11 years, there's sunspots. So sunspots is like erupting. It's called CME, coronal mass ejection. It like spurts off little bursts of energy off of the sun, and that's called a sunspot. And so we have high sunspots and high activity. During certain years, it goes up. There's a peak, and then it goes back down. And that cycle repeats every 11 years. So right now, we're just approaching the peak of the 11-year sunspot cycle this year into 2024 and 2025. And so after 2025, it's going to start to slow down. So when it's a high peak of the cycle, it produces a lot more electricity and ions and energy towards the Earth. And sometimes there can be solar flares that will actually charge the ionosphere. So if you've heard of the aurora borealis or northern lights, what it's doing is you got these energy coming from the sun, and it impacts the Earth's atmosphere, and it charges the particles, the ionosphere. And when it charges them, it produces like little curtains, like little fingers of curtains coming down, and is charging the ionosphere. So that's actually energy that you can see from the sun in this frequencies you normally can't see, like ultraviolet, and you can actually see them at night in the northern latitudes, like Alaska and further. So right now we're having a high intensity solar cycle. The aurora borealis has been observed as low as like Montana and Idaho, I understand, the last couple of months or whatever. But when they have these flares, you can sometimes see them even in the lower latitudes. And so what you can actually do with radio waves is you can say, oh, the ionosphere is charged. Let's point our radio towards it and use it like a mirror and bounce it off and go further off. So you can actually send your radio wave towards the aurora borealis at night, and then you can bounce radio waves off and go further. And because it's like little curtains, if you were moving, it's kind of like, it's called picket fencing. So you might be traveling down the highway and you hear this where you're talking, but it's kind of like high, low. They call it picket fencing. It has to do with the phase cycle of the wave. So you have an up wave and a down wave, an up wave and a down wave. And so what you're doing is you're picking up the high waves as you pass through the atmosphere. So the atmosphere travels and you have like this high periods of voltage or high frequency, high reception and low signal, high signal, low signal. And as you travel, that's called picket fencing. So now back to the previous page, 4-2. You have this figure 4.1. It's called interference patterns, knife edge diffraction. Okay, that's the answer. The question is something like, let me go find the question. Okay, it's T3CO5. Which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations? Okay, so basically if you have a signal going this way and you have an obstruction, and if it hits the edge, it'll diffract. Just like when you take like a stick and you put it into the water of a pool, it's straight, but it looks like it's bending. It looks like the stick is curved. Well, radio waves do the same thing. You put it through a diffractor and it can bend the other direction. So radio waves do the same thing as light, because light is also a wave. And so you can actually receive signals on this side of the barrier, even though there's an obstruction, because it diffracts and bends the signal down. And if you notice, there's these patterns where there's no signal, it's empty. So these are called the picket fences. And so you can see beyond the barrier on the other side because of knife edge diffraction. So that's a test question. And these dead spots, the distance between them is usually a half a wavelength apart. So if you're on the 6 meter band, then it would be half a wavelength would be 3. So these distances might be 3 meters or 18 feet apart. So every 18 feet, you might hear a high signal, a low signal, a high signal, a low signal. So it depends on the frequency you turn into about how often that's spaced out. So last week when we had my portable radio out here and we were listening to the net, Parmal just moved it from the window to the table and we got better reception. That's because the distance of the wavelength was a small part away and you got these like little bands of high and low energy. So it depends on where it's called phase, where the phase is on the frequency. So you might get a high signal and a low signal, a high signal and a low signal. So just moving it a little bit might give you a higher signal.
So is there a way to measure that?
Yeah, you can measure your signal strength. So on like the small radios, it'll have like, it's called a S meter. It goes from 1 to 9. So it'll tell you like how your signal is, how strong it is, or how weak it is. And so what happens is as your antenna picks it up, it induces a current. And then they take that current and that frequency and convert it into sound, if it's a sound. So it's just measuring the current received across the antenna is what it's doing. So it's the amplitude if it's an AM, or a frequency if it's an FM. So it just, it's measuring the amount of electricity that's passing across your antenna. So the longer the antenna, the more of the wave you're going to pick up. So it's a stronger signal. And the smaller the antenna, the less of the signal you're going to pick up. So just think if I'm putting this pen here and dipping it in the water, how much of these little rings am I going to put? If it's a small amount, I'm just going to pick up 2 or 3. If it's like the full pen, I might pick up all 10 of these. So you're going to get a stronger signal. So the length of your antenna and the direction it's pointed at will determine how strong your signal is.
Is there a point where that kind of, like, you talked about the 6 meter, you've got the 6 meter
Like band, yeah.
band.
Mm-hmm.
So a 6 meter antenna is like the best you could possibly get?
Yeah, or you can double it and get a 12 meter. So it's a multiple of the wavelength. You can cut it in half and have a half wavelength antenna of a 3 meter. So 3 meter, 3 times 3 would be 12 feet long. A quarter meter, a quarter wavelength would be 6 feet long, or an eighth of a wavelength would be 3 feet long. So like that portable one that I have was probably 3 feet or less. Actually, I think it's a 5/8 wavelength, but anyway, just for the sake of argument, let's say it was 3 foot. That would be like an eighth of a wavelength. The small handheld one might be like a 16th of a wavelength. So it's not very much, but you can still pick up the signal. So the interesting thing, what they do is the UHF is a small frequency, and then the VHF is a larger frequency. So what they do to make up the rest of the wavelength, you're like, that is definitely not, half of 6 meters would be, 18 feet. So it's not a 9-foot antenna, but it's like a 5/8 wavelength. So how come it's so small? Well, what they do is they take a wire and they wrap it around the base. They put a little coil, and that makes up the rest of the difference of the wavelength. So they have to make up the difference in the wavelength, and it has to be a multiple of the wavelength you're trying to receive. So the base of it is like a little thick part of it. That is the rest of the wavelength that's inside the base of the antenna. So they have little wires wrapped in there. The main part sticks out, but it's the same thing on the handhelds. They have little wrapping. You'll see like little wrapping around the flexible duck, rubber ducky they call them, flexible duck antenna. There's part of it in the base that's just extra wires wrapped around to make up the rest of the wavelength. So, I asked for questions and I didn't even hit start recording.
That's fine.
Oh no, I am recording. Yes, I am. Okay, I'm at 17 minutes. All right, so let's see, what else? I've talked about refraction. Okay, tropospheric inducting. So that was what I was talking about, where it can bounce between different layers. And what can cause that is inversion, temperature inversion, and cold and high fronts. So let me go back to, okay, it's 4-4, that page where it's got the different layers of the atmosphere. What causes those layers is temperature or high and low fronts. So that's called tropospheric induction or ducting. It creates a little duct or a pathway for the radio waves to bounce along. So you think of like an air conditioning duct. You put the heat in and it just stays in the duct and travels over time and then comes out the vent. The same sort of thing with the radio wave. It'll bounce, and when it finds an empty spot or it lowers the energy, it'll come out the other side and you can transmit your transmissions a long distance. So here in Utah, we have the inversion effect, which is the temperature inversion. So temperature can cause these layers of atmosphere. So that's kind of an easy one to remember, that it's temperature that can cause that. Let's see. Oh, another point to mention, back on 4-5, you've got this example of these high and low frequencies bouncing off the atmosphere or going through it. So why would you want to go through the atmosphere? Well, that's easy. You have a satellite above it, and you want to communicate through the satellite, right? So they use UHF frequencies, ultra high frequency, to go through the atmosphere so they can communicate through the satellite. So that's why they use UHF for the uplinks of the satellite. The sending data to the satellite is always UHF. And usually it's the VHF going down through the satellite. Once you're up in the atmosphere, you can go through, but it's harder to come out. So they use VHF for the downlink to receive the satellite signals, and then UHF for the uplink. So they're usually two different pairs of frequencies, an uplink and a downlink. Let's see. Oh, and then the band is said to be open or closed. That's on figure 4.5 or page 4.5. Open means you can transmit far, you can either bounce or reflect. The band is open. If you can send and receive, if the band is closed, it means you can't transmit. So that's just some kind of general terms. They also have some jargon here like DXing. I think I mentioned this earlier, but DX is distance. So long distance contacts are called DX. Let's see here. Last week I talked about this a little bit. T3B01. What is the relationship between electric and magnetic fields and electromagnetic waves? So it's in a 90-degree angle. So think of it as like the pages of this book. If I were to set it on the end like this top is like one is electro and this part is the magnetic. They're at a 90-degree angle. So the waves, electric might be this direction and magnetic might be this direction. So they're always at a 90-degree angle to each other like that. So that's the answer to that one. What's the relationship between electromagnetic? It's a 90-degree angle. All right, another part is polarization. Hey, Palmer, can you get me that handheld? Give me 2 handhelds. Any 2, it doesn't matter. Okay, so there's an idea of antenna polarization. So just like a battery has positive and negative polarization, an antenna has the same thing. It can produce positive and negative. Yeah, that's fine, just those 2. It can produce positive and negative energies. Okay, so for the sake of discussion, let's say this one is the repeater and it's way up here on the mountain. And here I am down in the valley and I want to talk to it. So what happens is if I am keying up or transmitting on one or the other, the radio waves are going to kind of go outward, just like a pebble in a pool, and it will produce waves this direction, and the other one will pick it up on the other side. Okay, so if I turn them this direction, this is called a polarization. It's either horizontal or vertical. So if the antenna up on the mountain is the repeater and it's got the antenna pointing up, I need to also point up so it can receive the signal and touch it on the other side. If I turn it this way, it's going to send it this direction, and they're going to be 90 degrees. One's electric, one's magnetic. You're going to have a weak signal. It's not going to pick it up very well. So if you were to hold your radio like this and try to talk to the repeater, you might have a hard time. But if you hold it like this, you'll be fine. So that's called the polarization of the wave. So the position of how you hold the radio and the way your antenna is pointed can determine the reception and the signal that you would get. Let's see if I have an example of a Yagi antenna. Okay, yes, 4-6. Okay, on 4-6, figure 4.4, they have what's called a Yagi antenna or a Yagi beam antenna. And I always remembered these in my earlier days because I'm old enough to remember VHF and UHF TV stations. I thought of them as TV antennas, right? Well, that's because TV was VHF and UHF. And so you may not have even noticed, but the beams on it's called, I can't remember what it's called, the leading element or the trailing element, the top and the bottom, it actually has a direction to it. So one of the beams is longer on the head than on the tail, and it's shorter.
I remember that with TV antennas.
Yeah. So it's basically what it's doing is it's directing the wave. So the longest wave is at the back, and the shortest or element or beam is at the front. So the shortest element is the direction that you're sending the radio wave, and the longest element is the back of it. So it's not where you're sending the radio wave. So think of it as like a backstop of like a pitcher, well, a catcher maybe in a baseball game. Your backstop is like your big wall. That's where you don't want the energy to go. You want it to go away from you. So it's the longer element is the opposite of where it's going. The shorter element is where it's pointing. So what you're doing is you're radiating, like let's say there was 2 pencils like this. Let's say these were beams. Pretend that this black one is the shorter one and the red is the longer one. It's going from the from the red to the black. It's going from the longer to the shorter, so it's going that direction. If you switch them, then it's going to go towards me because the shorter one's pointing towards me. So that determines the direction that you're transmitting or receiving. So now in the Yagi, they're going this way, so it's horizontally polarized. So you're going to send the energy that way. If you want to send it up in the air or laterally out in equal directions, you don't care about the direction, then you point it up. Or sideways. You might point it this way, or you might point it this way. One's horizontally polarized, one's vertically polarized. Okay, so you will see, for example, repeaters, like say this was one repeater and this is another. You might see a Yagi pointing this direction. So your beams would be this way instead of this way, vertical instead of horizontal, because you want to transmit from here to here. So if you want to go this direction, you might point it vertically. If you want to go out across the whole area, then you might point it horizontally. So it's called a radiation pattern with direction that the waves radiate outward. And so you will see vertically polarized Yagis in communication links. So for example, if you're driving down the highway, you may have seen those little weather stations in between the medians on the interstate. They'll usually have a Yagi antenna that's maybe this long. Sometimes they're really small. Well, they're pointed horizontally because they're going towards another link. So they're usually going that direction because they're just linking between different stations. All right, so let's see here. How are we doing on time? We're about 30 minutes into the second segment. Okay, I only want to go to about 4-9 and then stop. Oh yeah, okay, so we'll go to 4-8. So 4-8 shows you the radiation pattern. Okay, so if you were looking from the top down, so let's say, it's kind of hard to show, but if I'm looking this direction, the camera direction, so I'm looking from the top down, you're going to get the pattern on figure 4-5. And this is like a Yagi, so it's directional. So in this particular way, it's a bunch of Yagis pointing one direction. So it radiates outward. And because it's the long beam on the left half of this circle, let me illustrate here. So this left half would be where the long beam is, and the shorter beam would be the direction that it's going. So this is directional. And so if you're looking from it from the side, you have this figure 4-6. It shows you that it's going one direction or the other. So this one isn't a super great diagram. I just think of it as like a pebble in a lake. So this is it's called an omnidirectional antenna because it goes equally in all directions. There's no directing it. It's just going equally all the way around. If you want to direct the energy and point it a certain direction, you would get a Yagi. Like if I wanted to receive a station north in Salt Lake, I would point my Yagi north. If I wanted to receive my station in St. George, I would turn it south to receive and transmit that direction. So you can direct your energy based on the type of antenna and the way it's pointing. So in the old days, when I was living in Nebraska, we had UHF, VHF, and VHF only goes about 50 miles. And we were in rural areas, so our nearest TV station was like 20 miles away or more. And we had stations on one side and one on the other. And so depending on like, oh, it's 8 o'clock, I want to turn on to channel 3, and it's 10 o'clock, I want to turn on to channel 4, and they might be on opposite ends of where we're at. We had a little motor on the Yagi with a little feed line coming down, and you had a little dial, and you would just actually move it, turn it, and the Yagi would go, and motor would turn it. And it would point it towards that station, channel 3, and then at 9 o'clock came on, I want that show, I'd go and turn it towards the other channel to go to that station. And so you do the same concept in ham radio depending on what stations you're trying to contact. And if you're trying to use the atmosphere to bounce things off, or the ionosphere, or maybe the earth, or whatever. Okay, so I'm going to go into one little last piece, and I think I'll stop. 4-9, what happens to power lost in a feed line? On the top of 4-9, there's some questions there. A feed line is connecting the transmission of your radio to the antenna. So as you transmit your power, it can lose energy. What happens to that energy? Well, it actually turns into heat. So you can actually heat up a line, just like if you were to turn up too much electricity on your electric heater, or your blow dryer, you can feel the cord and you can actually feel it get hot. It turns into heat. Same thing happens on a radio. Put in a lot of energy into it, and if it's mismatched, I'll talk about that in a minute, then it can produce heat. And in the worst case, you can start blowing things out and have problems. So think about a pool in a wave pool. You go up and down. If you've seen those water parks, they have like a wave pool that goes up and down. They have something that disturbs the water and makes it go up and down. And depending on how often or the frequency, it can be a high wave or a low wave. Really fast up and down, it's going to be small waves. Really slow up and down, it's going to be big waves. So the same thing with your frequencies. You have a low frequency, high waves, and high frequency, small waves. Okay, so what happens is that energy travels along your feed line out the antenna, and it actually is kind of vibrating in the feed line up and down, and it can it's called impedance. So it's the amount of the frequency to the distance of your antenna and the length of your antenna. So if they're mismatched, it can actually cancel the waves and create heat, and you won't get a lot of your power out. It'll just refract back, and you're just not getting as much power outage. So you want to match the type of antenna to the length of your wavelength that you're sending out. So that's called a SWR, signal to wave ratio. So it's the ratio of your signal, your frequency, to your antenna, how big or short or long it is. So they have what are called SWR meters, and a perfect signal with minimal loss is 1-to-1. So let's say a 6-meter frequency in VHF band might be a 6-meter antenna. So if it's mismatched at like say 1.5 meters instead of 6, it's not a unit, it's not a multiple of the wavelength, and so it might be 1.5 SWR or something versus 2 or 3. The higher the mismatch, the higher the number. So 1-to-1 is perfect, 1-2 is worse, 1-3 is even really bad, 1-4 might blow out your unit. So they have these SWR meters that you hook up, and you measure it. A lot of modern day radios have equivalent of a fuse breaker, so if it's like 1.2 or higher, it'll just trip off to protect your circuit. Another thing that it talks about is coaxial cable, types of cables. So T9B02, what is the common impedance of coaxial cables? The answer is 50 ohms. So impedance is like the resistance in your feed line. So the higher resistance, higher ohms, lower resistance, lower ohms. And the reason they use, the next question is, why is coaxial cable the common feed line? Well, it's because the coaxial means two axes. So you have like your wire, and then you have a shield around it. Okay, like that, like a donut kind of thing, right? So inside is your conductor of one signal, and on the outside is the other conductor. And the way electricity works, it'll stay on the outside of the conductor. Coaxial is two axes of two conductors. One is on the outside, and one's on the inside. So there's two of them. You have to have a positive and a negative. And coaxial is used because it doesn't create a lot of interference. The signal will stay on the outside of the cable, and no matter what's next to it, it's not going to interfere with your signal. So they use coaxial because it's easy, and it also doesn't interfere with your signal, and you can put them next to each other. So those are some of the reasons why they use it. Also, all right, yeah, I think that's pretty good for today. I haven't really covered too many of the details of it, but that's a good overview, and that's a lot for today. And I think I'll stop. So thank you for tuning in this week. We'll continue next week. We'll do the second half of chapter 3 and the second half of chapter 4 next time.